Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss another one topic regarding momentum correction factor. So if you have seen our previous lecture, which we have discussed about the energy correction factor, and there basically we have discussed about the kinetic energy correction factor, and we also discussed about the correction factor. Now in this lecture, we are going to discuss about the momentum correction factor. So already I have discussed regarding the correction factor. What do you mean by correction factor? So this is nothing but a value which is used to adjust the value of accuracy. So when you do some kind of experimentation or will you do some kind of calculations, so there are some possibilities there, error will be there. To adjust that one, we used to consider a correction factor, because if you know the theoretical value and the experimental or actual value will never same. So to adjust that value, we used to use some correction factor. So this correction factor also used for the kinetic energy condition and for momentum also. So this momentum correction factor, actually it is defined. First, let me tell you, this is denoted by beta. So alpha was denoted by the kinetic energy correction factor, and beta is denoted for momentum correction factor. So this beta equal to, we can say, the momentum per second based on the actual velocity, based on same thing, just energy and momentum both are same, just we need to difference is their kinetic energy was there, and here we need to consider the momentum. Similarly here also, previously what I have written, momentum per second based on the energy per second, kinetic energy per second based on the actual velocity. Now I am writing momentum per second based on average velocity, So what is this actual and what is this average velocity is nothing but, suppose there is a pipe is there, and basically these things we are considering for the laminar flow condition or viscous flow conditions. So when there is a flow of liquid is flowing through a pipe, okay, particularly for pipe condition we are considering, and the flow will be like this, suppose, and in this pipe, if you see, we have number of particles are there, number of molecules are there which is flowing in this. Now this number of molecules having individual velocities are there, each particles having their own different velocities are there. Because if you see this velocity distribution, so how it distributed, so through the pipe it is it started from here, and it is maximum at the center of the point, and it is minimum at the surface of this pipe. So these things already we have discussed in the previous things. So what do you mean to say, if you measure the velocity of this individual particle, so that will be different, and if I take the average velocity of this, average velocity will be also different. That means here the velocity is different, here velocity different, here velocity different. So all the places velocities are different. So the average velocity of the fluid is different, and actual velocity is nothing but the individual velocity of the particle. Okay, so that will be different. So to find out this correction factor of the momentum, we need to take the momentum per second based on the actual velocity and based on the average velocity. So this need to be considered. So let's start this one. So now let's consider the small elemental area. This is the small elemental area. Okay, again for this also I need to draw this. If you have seen the previous one, you can easily understand. So here I am taking a small cylindrical path, cylindrical object you can say, and there, that is the circle for this out one, and this is the circle for this one cylindrical path, and another one circle is there, this one for this. So this one is the thickness of this or width of this part, and this is the outer circle radius capital R, and this is the inner one, you can say inside one, this is small r, you can consider this is the small one, inside one, this one small r, and thickness is dr. So let's consider the small elemental area, and through which the area is let's consider dA, and radius r, and the thickness, or we can say the width, is dr. Then we can say that area equal to dA equal to 2 pi r dr, 2 pi r dr, which is nothing but in the small elemental strip what is there. So the perimeter of this object and the thickness of that, you can consider this one. Now what I'll do, I'll just go for little fast, because similar kind of things we already have done. So the rate of fluid which is flowing through the ring, through this ring, flowing through ring, I can say, is equal to nothing but dq, or I can write it is AV, area into velocity, area of the ring element into the velocity. So this one we can write area equal to, already you got there, so that is nothing but 2 pi r dr. So this one also you can write dA, also you can write into the velocity u, you can consider, so u into 2 pi r dr. Now this is about the rate of fluid which is flowing through the ring. Now we need to find out the momentum. We know that what is the formula of momentum. Now momentum of the fluid per mass per second, momentum of the fluid per second equal to, we can write mass into velocity. So mass of the fluid into velocity. Now if you are going to consider this per second, then again here also you can consider the mass per second, and mass per second also you can write this is rho into q. So q, in the sense we can write rho into dq into velocity. So rho into, I can write rho into dq is nothing but this one, a into v, that is nothing but this one. So rho into 2 pi r dr into u into again velocity u. So if you want to write fully, I can write 2 pi rho r is there, u square dr. So this is the momentum of fluid flowing per second, momentum of the fluid per second. Now if you see, let's find out the total momentum of the fluid flowing per second, total momentum. So total in the sense we need to just integrate this value, integration of 2 pi rho r u square into dr. This is the equation. So total momentum of the fluid flowing per second across the section. So this across the section I'm telling. So now for this across the section means we need to consider from here to here the total. Okay, so that means not from here, actually we can consider throughout the section, means we can start from here, and from which point we are going to consider. So we can start from 0 value and we can consider up to r point. Okay, so from here to here we can consider. So that is total momentum, this one. So 2 pi rho u square r dr. So this is the, now here the twist point is we need to take the value of u. Okay, u, what this u is the actual velocity when the viscous fluid is flowing through a circular pipe, okay, or circular tube. So this equation, actually, if you have seen the previous video, we can get their value 1 by 4 mu minus del p by del x into r square minus small r square. So this is the value of this velocity, actual velocity actually. So now what we need to do is just need to put the value of this in this equation, that's it, and we need to solve this. Now again, if you have seen the previous video, it is easy for you, or else we need to go one by one. So what I'll do, I'll just go quickly. So let write 2 pi rho integration 0 to r. Again, just start writing this value, u value 1 by 4 mu, and this is minus del p by del x, bracket close. Again, r square minus small r square, bracket close, because whole square, because it is u square is there, so whole square is there. Again, r dr, this r into dr. Now again, just I can write this 2 pi rho bracket, whole bracket, again 1 by 4 mu, and I'm taking this value outside actually, del p by del x, bracket close. At a time also I can do it. Okay, let go for it one by one. So again, integration, because these are a constant term, I'm taking outside, that's why whole square, and integration, inside the integration what will be there, 0 to r, bracket start r square minus r square, whole square is there, into r dr. Okay, so now we need to solve it. So what we are going to get here, 2 pi rho, this is 1 by 4 mu, so this is whole square is there. So let's start writing 1 by 16 mu square, and this is del p by del x square, and whole integration 0 to r, integration r, this one again, a square minus b square, we can write the formula, that is a square plus b square minus 2ab. So here I can write r to the power 4 plus small r to the power 4 minus 2 r square, bracket close, and r dr. Okay, now this one again we can just write it here, 2 and this 16 we can cancel it. So what I can write, pi rho divided by 8 mu square, whole bracket, del p by del x square. Okay, now this is the term is going to be constant. Okay, and remaining terms we are going to be integrate. So let me write this again, 0 to r. So this is r to the power 4 into r plus r to the power 5 minus 2 into r square into r cube, whole bracket, dr. So now these things no need to write again and multiple times. So what I'll do, I'll just write this value here finally, pi rho 8 mu square into del p by del x whole square. This one let me keep it like this, and I'm just taking this value to this side so that I can do the integration directly. So what I'll do, quickly I just write integration part. I'll do the integration directly. So that is integration of r to the power 4 is constant. Let's take it outside, r dr. So r dr, so let me write here, bracket start. So this is r to the power 4 r square by 2. This is r dr, that is r square by 2, plus this is r to the power 6 by 6 minus 2r square is constant. So let's take it this out, and this is r to the power 3. R to the power 3 is nothing but r to the power 4 by 4. This is whole to the power r. This is the boundary condition 0 to r. So now we just put the value of r in this small r value. Then what will get, r to the power 4, this is r to the power capital R to the power 2. So that is nothing but r to the power 6 by 2. Similarly, already here r is there, that is r to the power 6 by 6 minus, if you see, the interesting thing is everywhere we are going to get r to the power 6 in the numerator, and here it is 4. Now again we need to solve this one. So this will be 12, and if you take common of this r to the power 6, and here what we are going to get, this is 6 plus, and this is 2, and this is minus 6. So here minus minus will be cancelled, 6 is going to be cancelled, 2 by 12, so we are going to get 1 by 6. So that is nothing but r to the power 6 by 6. The same value, just put it here, r to the power 6 by 6. And this one, equation, previously have I given any equation? No. So let's keep it equation 1. So now we need to find out the momentum of the fluid per second for the average velocity. This is for the actual velocity. This is the momentum for the actual velocity. So now we need to find out the momentum for the average velocity. So again, the same formula is going to be used. Momentum of the fluid flowing for per second based on the average velocity. Again, mass of the fluid m per second into the velocity. Now here the velocity we need to consider average velocity. So mass of the fluid, again I can write rho a v. So this one rho a v, I can write rho a u bar velocity into u bar again. So very simple, you can write rho a u bar square. Okay, so now here again one more tragedy thing, we need to consider the u bar value. So area A we can write pi r square. So write area of the circular tube, we can write pi r square, and u bar is nothing but, we can write actually u bar equal to the average velocity, which is nothing but u maximum divided by 2. Okay, because actually there what we got, u max by u bar equal to 2. Okay, for a circular pipe. So here I'm writing u bar equal to u max by 2. So what is the u max we got here? The same thing we can put it here. So now so let's put the value. Yeah, so what I'll do here, average velocity, and let's just put the value of u max. U max equal to how much? The interesting thing is u maximum equal to, just now I told, like 1 by 4 mu minus dp by del x, and this is r square. So okay, why we have taken the maximum velocity? See, here I have taken the value of u equal to this one. So this one, this equation, only difference is r square, this small r square, and here only r square minus r square is there, but here only r square is there. So u maximum, when the maximum velocity we can get it, now when the r value, the radius will be maximum. That means when you get the r, which one, the radius r at this point, r equal to 0. Okay, at this point we are going to get the maximum velocity. That's why this r distance is, this r equal to 0 here. So that's why we are getting this one. Okay, so now we can write u max by 2. So we can write this directly. I can write here 1 by 8 mu, because u max by 2, 1 by 8 mu minus del p by del x into r square. So this is the value. Now we need to find out the momentum, as I told you, momentum per second of average velocity. So the same thing, let's write here, momentum per second based on average velocity. I can write again the formula rho pi r square, rho pi r square, a value I've written, a value pi r square, and u bar square is nothing but this equation total. I need to write this one whole. So let's write 1 by 8 mu bracket start del p by del x minus this is r square, capital R square is there, and whole bracket, this is closed. So now this is the momentum per second based on the average velocity. So if you want to solve this also, you can solve it like, let's just elaborate this one. 8 mu is there. So rho a r square divided by this 8 mu is there, that means 64 mu square, and this is minus del p by del x whole square into r to the power 4. So r to the power 4, r to the power 4, this will be r to the power 6. So this is the momentum per second based on the average velocity. This is one, and this is for actual velocity. Now based on our definition, so what we need to do, we just need to find out the value of beta. So beta, what is the formula I told? So formula is this one: momentum per second based on the actual velocity divided by average velocity. So it's quite simple. Just you put this value. What we got, pi rho and by 8 mu square. 8 mu square minus del p by del x square into r to the power 6 by 6, r to the power 6 divided by 6. So this is actual one. Now here we'll get rho pi, this is pi, or you can write pi rho divided by 64 mu square, 64 mu square, and here we can write 64 mu square minus del p by del x whole square, r to the power 6, r to the power 6. Now if you see, we just can cancel all these terms, and finally what we are going to get, this pi rho cancel it, mu square cancel it, r to the power 6 cancel it, del p by del x square cancel it. So what are the remaining terms are there? If you see, 8 into here 6 is there, 48, and here 64 will go up. So this is 64 divided by 6 into 8, that is 48. So if you solve this, 16 into 4 and 16 into 3, 4 by 3. So beta value is here 4 by 3. In the previous case we got energy factor, there alpha we got 2. So here we are getting this beta momentum factor, this is 4 by 3. So this is all about the momentum correction factor. So I hope you understand this derivations, though it is a lengthy one. So concept is similar for energy, kinetic energy correction factor and momentum energy correction factor when it is flowing through a tube in a pipe, you can say. So what are things we have considered? Rate of fluid flowing through the ring and momentum of the fluid per second, then the total momentum. See, first step, second step, and this is third step, and this is third. After that, fourth one, this one fourth step, and the final one, this is the final one, sixth step, number 6. So I hope you understand this concept of this momentum correction factor, and if you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you all.